Hi, Assalamualaikum. My name is Hafratul Abida and my metric number is KA22065. So today I'm going to explain the introduction of electroplating industry. So electroplating is a manufacturing process that uses electric current to coat a thin layer of metal onto another material. It enhances product performance by improving corrosion resistance, durability, electrical conductivity, and surface appearance, widely applied in industries such as automotive, electronic, aerospace, construction, and jewelry manufacturing. The process generates wastewater containing heavy metal, acid, suspended solid, and other pollutants that can harm the environment. Proper wastewater treatment and sustainable waste management are necessary to meet environmental regulation and protect public health. That's all from me. Thank you.
Electroplating wastewater is generated from cleaning, acid picking, plating, rinsing, and finishing operations. According to our project specifications, the wastewater flow rate is 100 cubic meters per day. The wastewater is highly acidic with a pH of 3.0 and contains moderate organic pollutants with a BOD of 150 mg per liter and a COD of 650 mg per liter. It also contains high suspended solids, oil, and grease, ammonia, nitrogen, and potentially toxic heavy metals such as chromium, nickel, copper, zinc, cadmium, and lead. Due to its complex composition, a combination of physical, chemical, and biological treatment processes is required to effectively treat the wastewater. The major pollutants in electroplating wastewater each create different environmental problems. First, the low pH makes the wastewater highly corrosive and increase the mobility of heavy metals. Organic pollutants represented by BOD and COD consume this of oxygen during decomposition, which can harm aquatic organisms. Highly suspended solid increase water turbidity and lead to sedimentation accumulation. Oil and grease form a thin layer on the water surface, reducing oxygen transfer. Ammonia nitrogen is toxic to aquatic life and contribute to eutrophication. Finally, heavy metals are the most concerning pollutants because they are toxic, non-biodegradable, and can accumulate in living organisms through the food chain. In summary, electroplating wastewater presents several treatment challenges. The acidic wastewater must first be neutralized before further treatment. Suspended solids, organic matter, oil and grease, ammonia nitrogen, and especially toxic heavy metals must be effectively removed. Since no single treatment method can eliminate all these pollutants, an integrated treatment system combining physical, chemical, and biological process is proposed. This approach provides effective pollutant removal while ensuring compliance with environmental discharge standards. Treating wastewater can cause serious environmental problems if it is discharged without proper treatment. The main concern is heavy metal pollution, as metals such as chromium, nickel, and copper are toxic, non-biodegradable, and can accumulate in the food chain, posing risk to both ecosystem and human health. In addition, the highly acidic wastewater can lower the pH of rivers and increase the toxicity of heavy metals. Organic pollutants, suspended solids, oil and grease, and ammonia can release dissolved oxygen, increase water turbidity, and contribute to eutrophication, which negatively affects aquatic life. Untreated wastewater may also contaminate soil and groundwater, creating long-term environmental problems. Therefore, an effective wastewater treatment system is essential to minimize pollution and protect both the environment and public health.
My name is Li Chaowei, metric ID KA22085. Next, I will present about Chapter 4, Selection of Treatment Process. For this electroplating wastewater treatment design, the selected treatment process is based on the wastewater characteristic. The wastewater flow rate is 100 cubic meters per day with strongly acidic pH of 3 and high suspended solids concentrations of 450 milligrams per liter. Since electroplating wastewater contains heavy metals and chemical contamination, physical-chemical treatment is selected because it is more effective for heavy metal removal and suitable for acidic wastewater. The first treatment unit is the utilization tank, which balances fluctuations in wastewater flow rate and pollutant concentration. This is important because wastewater generation from plating and rinsing processes is intermittent. Next is the neutralization tank, where sodium hydroxide is added to increase the pH from acidic conditions to around pH 8 to 10. This promotes metal hydroxide precipitation and improves heavy metal removal. After neutralization, coagulation and flocculation are carried out. Coagulants such as alum are added to destabilize suspended particles, while polymer enhance formation. This process is important for reducing high total suspended solids. Then the primary clarifier separates the formed flux through solid-liquid separation, removing metal precipitate and suspended solid effectively. After clarifications, the wastewater passes through a sand filtration unit. This acts as a polishing step to remove remaining fine suspended particles and improve effluent clarity. Then the activated carbon adsorption provides final polishing by removing residual organic compounds, color, and trace contaminants. This helps improve final effluent quality before discharge. Before discharge, chlorination is applied as a disinfection step to eliminate remaining pathogenic microorganisms and ensure compliance with environmental discharge standards. Meanwhile, sludge generated from the clarifier and sand filter backwash is collected for flush management. Since the sludge contains heavy metals, it is classified as scheduled waste and requires proper handling. For sludge treatment, a sludge thickener is used first to increase solids concentration and reduce water content. After thickening, the sludge is sent to a filter press for dewatering, producing sludge cake with lower moisture content. Finally, the sludge cake is disposed of at a licensed scheduled waste facility, while filtrate can be recycled back into the treatment system. Next, this process flow diagram summarizes the complete wastewater treatment system, where the wastewater first enters the equalization tank, followed by coagulation and flocculation with chemical addition. The wastewater then undergoes clarifications, sand filtration, activated carbon absorption, and disinfection before discharge. At the same time, sludge generated from the process is treated using sludge thickening and filter press before final disposal.
Hi, my name is Sultana Azira, and today I will present the basic sizing of major wastewater treatment units. So first is the equalization tank. Equalization tank is designed to equalize the fluctuation in wastewater flow and concentration before the treatments. So the sizing starts by determining the influent flow rates and selecting an appropriate hydraulic retention time. So for the design, a retention time of 6 hours was selected. The tank volume then was calculated using the flow rate multiplied by the retention time. After obtaining the volume, the tank dimensions are determined by assuming the suitable liquid depth and calculating the required surface area. Finally, the diameter, height of the tank are calculated to provide the required volumes. So this is the data sheet for equalization tank. After equalization, the wastewater enters the coagulation and flocculation units. For the coagulation tank, a short retention time about 1 until 5 minutes are normally used because rapid mixing is required to disperse the coagulants. The tank volume is calculated using the flow rate and detention time. For the flocculation tank, a longer retention time is around 20 until 30 minutes is selected to allow particles acceleration and flow formations. Using the same volume equation, the required tank volume and dimension are obtained. Next, the primary clarifier. Primary clarifier removes suspended solids through gravity settling. So the sizing is based on the surface overflow rates, which represent the hydraulic loading applied to the clarifier surface. First, the required surface area is calculated by dividing the influent flow rates by the selected overflow rates. Once the area is known, the clarifier diameter can be determined assuming a circular tank. The site water depth is then selected according to standard design recommendations to complete the sizing. So this is the data sheet for primary clarifier. The sand filter is used to remove remaining suspended solid after clarifications. The key design is the filtration rates. The required filter area is calculated by dividing the wastewater flow rates by the selected filtration rates. After obtaining the areas, the filter dimensions are determined. Additional design considerations include the sand depth, gravel, support layer, and freeboard to ensure the effective filtration performance. So this is the data sheet for sand filter. The activated carbon absorber is designed to remove dissolved organic contaminant color odor from the wastewater. Sizing is based on the empty bed contact time or EBCT. The required carbon bed volume is calculated by multiplying the flow rates by the selected contact time. Once the bed volume is obtained, the column diameter and height are determined. Activated carbon depth is selected based on the typical industrial wastewater treatment design practice. So this is our activated carbon absorber data sheets for specifications. The sludge thickener is used to increase the solid concentration before dewatering. The sizing is based on the solid loading rates. First, the daily sludge production is estimated from the treatment process. The thickener surface area is then calculated by dividing the solids by the selected loading rates. The tank diameter is determined from the calculated area. Finally, the site wall depth is calculated by considering the freeboards, clean water zone, setting zone, and thickening zone. So this is the sludge thickener data sheet. So lastly, the filter press. The filter press is the final sludge dewatering unit. The design begins by estimating the sludge volume generated by every day. Next, the slurry volume process per cycle is calculated based on the number of operating cycles per day. Using manufacturer data and filter press sizing charts, the required filtration is determined. After obtaining the filtration area, the appropriate filter press size is selected. In this project, an 800 meters filter press which approximately 20 chambers was chosen to handle the sludge production at rate. That's all from me. Thank you.
Hi, Assalamualaikum. My name is Electroplating, and my metric number is KA22065. So today I'm going to explain the estimated cost of treatment system. So the equipment cost is calculated for each main equipment in this project. To calculate the purchase cost of the main equipment, the equation below was used, which is log 10 CP equal to K1 plus K2 log A plus K3 log A times 2, where A is the area of equipment. The data for value K1, K2, K3 can be obtained from 13 book 2003. And the bare model cost can be calculated using the equation below, which is CBM equal to CP times FBM, where P is the pressure of the equipment. The data value for C1, C2, and C3 can be obtained from 13 2003 books. Also, the cost for selected equipment is summarized in table 7.1. And the total cost of the equipment is 7.2 million ringgit Malaysian.
So this is the overall cost summary for our cost of treatment system. Our capital cost is 13 millions and our O&M cost is 563,000. Our chemical cost is 108,000. Our sludge disposal cost is 249,000. So it's come to the total annual operating cost, which is 920,000, which is the formula is to plus O&M cost, chemical cost, and the sludge disposal cost.
Section 8 discusses the expected treated effluent quality of the proposed electroplating wastewater treatment system. The treatment chain consists of equalization, neutralization, coagulation, flocculation, clarification, sand filtration, activate carbon adsorption, and disinfection. During neutralization, dissolved heavy metals such as chromium, nickel, and copper are converted into insoluble metal hydroxide. These metal particles are then removed through coagulation and sedimentation process. The sand filter acts as a pollution unit to remove fine suspended solid, while activated carbon adsorption removes residual organic compounds, color, and trace contaminants. Finally, the disinfection process eliminate any remaining microorganism before discharge. As a result, the treated effluent is expected to comply with the Environmental Quality Industrial Effluent Regulation 2009 Standard B and minimize environmental and public health risks. Section 9 focus on sustainability and sludge management. Several sustainable features have been incorporated into the proposed treatment system. First, the equalization tank balance fluctuation in wastewater flow and pollutant concentration. This improves treatment efficiency and reduce chemical consumption. In addition, the inclined plate clarifier requires less land area compared to conventional sedimentation tanks, making the design more compact and space efficient. This feature improves operational reliability while minimizing secondary pollution and environmental impacts. In conclusion, the proposed electroplating wastewater treatment system effectively removes suspended solid, organic pollutant, oil and grease, and heavy metals through a combination of physical and chemical treatment processes. The system is expected to produce effluent that meets Malaysia's Standard B discharge limit while ensuring safe sludge management. Overall, the design provides an efficient and sustainable solution for protecting the environment and supporting responsible industrial operation. That's all from me. Thank you.